Hey everyone, in the previous video we spoke about adversarial search and its applications. Today we're going to talk about one of the algorithms which are there in the adversarial search called MiniMax algorithm. What exactly is MiniMax algorithm, right? So imagine you're playing a game of Catan or maybe any game like a snakes and ladder game as well, right? In any kind of game, what you're trying to do is you're trying to maximize your probability of winning. Similarly, on the other hand, your opponent is trying to minimize your probability of winning, right? So that's how the name is called MiniMax algorithm, where there are two opponents in this case, and the mini player is trying to minimize the probability of winning of the other player, while the max player is trying to maximize the probability of winning the game, right? That's why it's MiniMax. It's primarily applicable to any kind of games that you play where we have multiple opponents and multiple teams involved, right? Let's understand what MiniMax algorithm does and how it works with a very quick and easy example. Let's dive in. So let's take an example of Tic Tac Toe. Imagine you're player X and your opponent is player O. There are three final stages to any kind of game. You can either win a game, you can lose a game, or the game can be tied out. And as for any games, you have points for each game, right? So let's say if you win, you get 1 point. If you lose, you get -1. And if you tie, you get 0. Simple enough. Now let's take an example of Tic Tac Toe. Imagine this is the current state of a Tic Tac Toe game, right? And now it's the opponent's chance to place. Now the opponent can either play on the bottom middle place or on the top left place, right? So again, in this case, there are two cases, case 1 and case 2, that can emerge from the current state. So let's draw out those two cases. In case 1, where the opponent is playing on the top left corner, there is only one other case where the X can play, or one other option where the X can play, which is the bottom middle. So the X will play there. In case 2, where the opponent has played in the bottom middle position, X only has one option to play, which is the top left. Now, till now, we have explored all the different scenarios in which this game can be played to reach a final state, right, from the current state. So in case 1, the final state reached is where the X has won. So, and imagine X is you, right? So in this case, you have won and you will get 1 point. As mentioned above, the final states and the points, right? In case 2, the game is tied, so you will get 0 points because no one has won the game. So for tying, we give 0 points. If you've understood till now, that's basically the crux of what MiniMax algorithm is, right? Now let's go one step ahead. Let's go one level above and try to see who was supposed to play. So at this level, X was supposed to play the game. Basically, you were supposed to play a game, right? Or you were supposed to play your chance. And as you are the max player, you'll try to maximize your probability of winning the game, right? So what you'll do is at each case, you look at your children and you'll see that, hey, what is the max state of my children? In this case, there's only one children, hence the max will be the value of that particular children, that is 1. In case 2, you will again look at your children and you'll see, hey, which children is giving me the max state? There's only one children, hence the value will be the value of that particular children, that is 0. Now let's go one level above, right? One level above, who was supposed to play the game? Your opponent was supposed to play the game. And what is your opponent trying to do? Your opponent is trying to minimize the probability of you winning, right? So what will the opponent do? The opponent will look at all the children and try to see which children is giving them the minimum utility or the minimum value. Now in this case, there are two children. One children has the value 1. The second children has the value 0. The minimum of 1 and 0 is 0. Hence, the value for that particular state is 0. Once you've given values to each of the states available in the game, it's simple. So now the objective of the game here is to finally identify, given the current state, what is the most probable route that the game will take before it reaches the end. And to find out that, what we have to do is basically take the values that we got from each stage. So from the first stage, we got a value of 0. So basically it says that it will go to the route which is giving them the 0 value, which is case number 2. In case number 2, the value is 0, which means it will go to the route which is giving them the value 0, which is the children of that particular level. This is a very simple case where we have few scenarios, but you can expand this to multiple scenarios and you can also take it one level above, where here the current state is already where most of the boxes are filled and only 2 boxes are left. Imagine you're taking your current state as a blank slate, right? In that case, the number of possibilities of different scenarios will be huge, and that's where the MiniMax algorithm can be expanded. So this is a very basic level at which the MiniMax algorithm works, but you can apply the same algorithm or same principle to a broader set of games, right? If you look at books or any resource online, instead of representing state like these, they will represent states in the form of triangle, an upward facing triangle and a downward facing triangle. A downward facing triangle basically says it is the minimizing state, something like this in our example. And the maximizing state is denoted with the upward facing triangle, something like this state in our example. So again, don't get confused if you see a upward facing or down facing triangle in books or any other examples. It's just the same principle. So again, here the objective is finally to understand what route should be taken or what route is the best possible route that will get you to the final state, which can either be a win, lose or a tie state. In the upcoming videos, we'll talk about how to optimize this algorithm, right? Because one of the disadvantage here is in this case, you are basically listing out all the states of the game. Imagine you're playing Catan. In a game of Catan, there are hundreds or thousands of states or scenarios from the current state that you can take, like thousands of possibilities from one state to reach the another state, right? So in that case, this kind of algorithm becomes really inefficient and involves a lot of computing power. Alpha beta pruning is an optimization algorithm that we can apply on top of this MiniMax to kind of make this algorithm more efficient. We will delve into that algorithm in the next video, so stay tuned. Thank you for watching.